Okay, so yeah, so let's get started. Hello, everybody. So we are very happy to have Professor Isa Hafalir from University of Technology Sydney. So he's visiting for basically this week, sitting on the sixth floor. So hopefully you have a chance to talk to him. All right. Anyway, so the lectures begins today and continues until Friday.
Yes.
Okay. So I guess without too much further ado, so I should give you the chance to talk, Isa. So please go ahead.
Thank you very much. Thank you, Tito, for the invitation. I wanted to be commercial Tokyo Market Design Center and visiting here. So we are going to have 1.5 hours class today and 2 more on Friday. So plan is basically in today's 3 hours. I'm going to go over basically Vijay Krishna's Auction Field book, first 5 chapters, most of them. Okay, but not every detail, but most of the content that. This is gonna be the what we will cover today. On Friday, I'm going to talk about basically 4 papers. 3 of them actually were published in the past, so it was not recent. One of them more recent, still in the publication process. So those in the first 1.5 hours, I'm going to talk about the auctions in pre-sale work that Vijay and I had done. And the second class is going to be about 2 more papers. One of them is about multi-unit auctions with budget constraints. And the second one is about like a special fish auction. And there is also an experimental part in it too. All right. So please feel free to interact at any point. There will be some material on the slides, but I'm going to also write some other stuff that are not in the slides on the whiteboard as well. All right. So auction theory. So auctions have been used in practice for a long time. And Vijay's book actually starts with this, interesting story about Roman Empire at some point was actually even auctioned off. And I forgot the name, but a politician or a warrior, a general, bought the whole Roman Empire and beheaded in 2 months. And Vijay calls this one of the earliest and most extreme instances of winner's curse. And in Babylon, the slaves were used to be sold via auctions, and now also everywhere we see everywhere the auctions everywhere, right? So the most common examples are the procurements that are done by the governments. Procurement is a negative auction, so you do not sell an object, but you buy a service. But most of the laws of the countries actually require some kind of competitive bidding in order to get any service. So auctions are used. Auctions are used for selling keyword advertisement auctions. Now it needs to be changed a little bit because we are with the age of the generative AI and generative AI agents. We are more or less going to no-click internet, so these need to be changed a little bit. But the internet advertising is a big application of auction theory. The bonds of the countries are sold via auctions. Spectrum auctions are a very important application. There are so many examples of auctions. So it's an important application of market design, right? So it's like a real hand-on, practically very important. And some of these, like the things that I will tell you, maybe it's going to be obvious to you. Some we go into more details, but I want to basically assume some knowledge of game theory, but not necessarily advanced level of game theory. So we will model auctions as Bayesian games, and Bayesian games, as you know, are the strategic environments in which people hold some private information, and then they interact. And the first thing that we need to understand is what kind of valuation structure we consider. And the 2 examples are private values and common values. So in today's class, basically, we will almost exclusively consider private values. So what does private value mean? Private value means if you are participating in an auction, your value by winning this object, consuming this object, just depends on your own taste. Okay. Whereas common values on the other extreme is there is a common value that is the same for everyone, but people, like different bidders, may have different estimates about it. And the standard example for that is like mineral rights model, in which like a piece of land is sold and everybody has the same resources in terms of how much oil is underneath. But in the real world, actually, almost all the case, there is some private value element and there is common value element. But private value element is like in auctions, is important to understand at the beginning. So we will start with the private values model, and the 4 auctions that is very commonly used in both in theory and practice are 2 of them are the open formats. So these are dynamic auction formats, and 2 of them are sealed bid formats. So these are like simultaneous move games. And let's start with the Dutch deciding price. So Dutch deciding price is used to sell, for instance, fresh produce such as fish and flowers. And the name actually comes from this being used to sell flowers, particularly tulip, in Netherlands. So that's why it's called the Dutch auction. So the price starts from a high and it starts going down up until somebody says mine. Okay, this can be done orally, this can be done with like in an electronic system. But the idea is high starting price goes down up until somebody claims the item. Other one is English ascending price, and there are different variants of it. But let me talk about, since I'm in Japan, let me talk about the one that is called like Japanese button auction, Japanese version, which is the price starts from below and it continues to go up until at least 2 people are interested, 2 bidders are interested in the item. And when there is only one, so they basically leave either like releasing the button or just like lowering their hands. And at the point in which there is only one interested bidder, then the price stops. That person is the winner, and that price is the sold price. Okay, that's the English. And there are different versions, as I told. Like it could be English outcry, right? For instance, like the price starts from below, low values, and rather than an increase in the prices automatically, people can shout out the new and higher numbers, or auctioneer can shout out higher and higher numbers. There are some differences between them, but the idea is like a dynamic auction format starting from low price and going upper, right? And on the right hand side we have first price auction as second price auction. First price auction, especially the procurement version of it, is very commonly used. So the idea is that these are called also like sealed bid formats, because the bidders, they actually write their bids on a piece of envelope, and this is opened, right? So like at the time of the bidding, nobody knows each other's bid. And first price auction is simple. The highest bidder wins, and highest bidder pays her own bid. That's why it's called first price, the first highest price. The second price auction, which is like first proposed by Vickrey in the 1961 seminal paper. And at that time, actually, many people thought that this was not used in practice. So it was like a theoretical one, but actually like later, I think some papers have actually found that some kind of version of it actually had been used for selling stamps, like antique stamps. And the second price auction works again as a simultaneous move game. The highest bidder wins, but this highest bidder doesn't pay her own bid. It pays the second highest bid, or the highest losing bid. So that's why it's called the second price. And the first observation that we will make is that these 2 auction formats, Dutch deciding price and first price auction, they are strategically equivalent. So what does 2 games being strategically equivalent means? It means that from the set of strategies in one game, I can basically have, except for redundant strategies like duplicate strategies, I can have a one-to-one correspondence between them. And basically the strategies and outcomes are exactly equal to each other. And we can see this by thinking about the set of strategies available in a first price auction. What is my strategy? The strategy is what to write in this piece of paper, right? And if I win, I will have to pay what I write on this piece of paper. Whereas in a Dutch auction, my strategy is when do I, when do I stop the clock if the clock hasn't been stopped before? And you can see that there is actually an equivalence between them. So these 2 auctions basically are the same auctions in terms of strategic perspective. So if we solve the Dutch auction, then we are also solving a first price auction. If we are solving a first price auction, we are also solving the Dutch auction. Whereas there is a very big similarity between English auctions and second price auctions, but it is not strategically equivalent. Why it is not strategically equivalent? Because like think about the strategy in a second price auction. Again, it is like what to write on this piece of paper. But in an English auction, you think about when to release the button, right? Like the price is increasing. But at the time that you are deciding to release the button, you actually have some observations, right? Because you see, like let's say that there were 10 bidders and there is now only 3 bidders left. But you actually observe when does the bidders drop out. And if you are in an environment in which you have some common values element, it's not a purely private value element, like you care about other people's, other bidders' signals and therefore values, then actually, once you are observing when they are dropping out, you actually change your estimate, right? So they are not strategically good. So in a private values case, we can say that these two options are the same, but without private values, we cannot say that these two options are the same, right? So, yeah, Milgram and Weber, like, observed this.
I'm very embarrassed to ask this question, but I usually get confused. So why, I think you explained why the English auction, second price auctions are only equivalent under private values.
Yes.
And so why does that problem not happen between Dutch and the
I did not explain that well, so that I think it was a good question that you asked, because in a Dutch auction, you don't observe anything, right? So in an English auction, you observe when bidders drop out, but in a Dutch auction, think about common value environment, right? Common value environment or like an interdependent value environment. As soon as you push the button, the game ends. Mm-hmm. And as soon as somebody else pushes the button, the game ends. So there is no chance of changing your valuation.
I see.
That's why.
So observing that nobody has pushed the button tells me something about the value, but when there are no variation in the
so basically, like the new information comes from what happened prior to my decision, and in a Dutch auction, prior to my decision, nothing happened.
I see.
Yeah.
Thank you.
So am I right that the English and second price are equivalent if there are only 2 bidders?
Yes, it's a very good point. Yes, very good. I forgot to say that. Actually, I think in VJ's book there is this something called private values or n is equal to 2, which is exactly going back to our previous discussion. When there are only 2 bidders, even when the price is going up, at the time that something happens, the game ends. So there is no new information. So this holds when there is private values or when only there are 2 bidders. Very good. Thank you. I forgot to say that. All right. So what is the simple model that we will start talking about, and basically most of the class will be about this, is single indivisible objects. So this is like single unit options. Of course, there is a very important application of multi-unit options or multi-item options. I will not talk about them today, but one of my papers that I will present on Friday will have multi-unit options, for instance. We will have risk neutral bidders. So we have a finite number of bidders. And at the beginning, we will talk about these bidders having risk neutrality. That later today, we will talk about, for instance, what happens when we have risk averse bidders. And each bidder draws their value. This capital X will represent the random variable of bidder I, capital X sub I. But this distribution of this random variable is F. So it doesn't have an index of I. So this means that we have a symmetric model. We have a model in which all the bidders draw their values from the same distribution F, and these are independently drawn. So we are not currently considering interdependent, value structures. And of course, the realized value is privately known, and the number of bidders and the distribution of the private values is common knowledge. Okay, so and whenever we are talking about options, we also tend to compare them, right? And the 2 most important comparison of different auction formats is the first one is from the seller's perspective, which is the seller's revenue or the expected revenue or the expected selling price. And this is, of course, very important. And the other one is efficiency. Efficiency is the sum of the utilities of all the bidders. So it's a social welfare. Okay. of course, there are other measures we can think about, like for instance, the options that are better performing in like collusion, or like there is like a core deviation options and other stuff, but the revenue and efficiency are the most standard ones that are considered. All right. So let's start with the second price auction. So as a game in a second price auction, utility of bidder I, who has a value of X and who bids B, is equal to, and let's say that like let's call these bits by capital like this. This B as a vector of all the bits is B minus maximum of I not equal to J, B J, then BI is strictly greater than the maximum of I not equal to J not equal to I, J not equal to I. Okay. So if I'm the highest bidder, then I pay the highest remaining bid, which is the second highest bid, and otherwise it is zero. And let's say that and this is equal, the ties are broken randomly. So if there are like two or more bidders who have the same highest bid, then with equal probability I will give to one of them. And it is very easy to see that in this Bayesian game, although you may potentially consider like Bayesian-Nash equilibrium, there is a stronger equilibrium that is happening, which is bidding the value is a dominant strategy. Okay, so therefore, everybody truthful bidding or bidding their values will be a dominant strategy equilibrium, therefore a Bayesian-Nash equilibrium as well. And to see that the bidding the value is dominating underbidding or overbidding, we can look at this figure. So let's say that the highest bid among my opponents is Z1, okay, and I'm sorry, I have a value of X1, and I'm considering something, bidding something smaller than X1, Z1. So if the highest bid among my opponents is in this region, which is smaller than Z1, then I am indifferent between Z1 and X1 because under both cases I win, and under both cases I pay the same, right? Because I only pay the second highest bid. If the highest bid among my opponents is in between this Z1 and X1, then with X1 I win and I pay something smaller than my value, so I get a strictly positive payoff. But with Z1 I lose, therefore I get zero. So it's a missed opportunity. And again, if the highest bid among my opponents is greater than X1, under both cases I lose. So here it is the same, here it is the same, and here truthful bidding is strictly better than underbidding. Therefore, truthful bidding dominates underbidding. And similarly, you can do the same for overbidding. So this shows that overbidding and underbidding is dominated, and therefore truthful bidding is a dominant strategy equilibrium. Okay. Does this mean that this is the unique Bayesian-Nash equilibrium? Anyone? Let's make this more interactive. So there is a dominant strategy equilibrium, but can there be other equilibria? Yes, Rito.
Maybe sometimes there's an equilibrium in which one person bids very high and everybody bids
So like think about
something.
two bidders, uniform 0-1. Then let's think about one bidder bidding 0 all the time for all values, and other bidder bidding 1 all the time for all values. You can see that this is an equilibrium. Why? Because the 0 bidding bidder, let's say that this is bidder 1, this is bidder 2. Bidder 1 is losing, and in order to win, this bidder needs to bid higher than 1, which will make a negative payoff. And similarly, bidder 2 has no incentive to deviate to anything else because winning and paying the price of 0. Actually, there is a paper by Bloom and Havidas, I think, that shows that in this setup, all the equilibria will be something like this. So let's say it's 0 to 1, up to some value k. This bidder is bidding 0, and this bidder is bidding k. And after k, they are truthful bidding. So this is the set of all equilibria in second price auctions. I think there was a paper like this. All right, so but whenever we talk about equilibrium of second price auction, we talk about the dominant strategy equilibrium, and we ignore these inefficient equilibria because we are using simply the equilibrium refinement of not using dominated strategies. Any questions? All right. So let's go. Okay, before that, let me also write. I will come back to this, but in a second price auction, like the main result of the first class is going to be something like revenue equivalence theorem that most of you may know, but in that one we are interested in interim and ex ante expected payments, right? So I can write down the interim expected payment in a second price auction of a bidder with value x as, let me define g of x as f of x to the power n minus 1. All right. So what is the interim expected payment in the truthful bidding equilibrium of a second price auction? So let me remind you, ex ante, ex post, and interim and ex ante, right? So interim means I know that my value is x, and I am trying to basically I'm taking an expectation of my expected payment to the auctioneer. All right. If I have a value of x with probability g of x, I am going to win, right? Because I win since I am truthful bidding and everybody else is doing the truthful bidding. The only case that I will win is when everybody else, n minus 1 opponents, they all have values smaller than x. Therefore, with probability f of x to the power n minus 1, that I denote by g of x, I'm going to win. Okay. And then I am going to pay the highest of basically like highest of n minus 1 random variables. This is how we denote it. Y the highest of n minus 1. Okay. N minus 1, given that this is smaller than my value. Okay. So this is going to be the interim expected payment in a second price auction. Now, having noted this, let's move to a little bit.
So that's my payment, or
that is your interim expected payment of any bidder with value x. Okay. And let's now look at like the equilibrium in a first price auction is not as simple. And let's start with a simpler example. So let's say that we will in the next slide we will do basically the general case. But let's think about we have only two bidders and the value distribution is uniform. And let's assume an equilibrium or conjecture an equilibrium in which the bidding strategy is linear. So beta of x is c times x for some c. So let's consider basically bidder 1 is assuming a bidding function of bidder 2 equal to cx. And this is the maximization that the bidder 1 will do, right? So bidder 1 will choose some p in order to maximize the probability of winning times, in the case of winning, the utility is x1 minus p. And the probability of winning with a bid of p is probability that beta of capital X2, which is the random variable that denotes bidder 2's value, is smaller than b. But this beta of x2 is just c of cx. Therefore, this just becomes cx smaller than b, which means cx2 smaller than b, which means x2 smaller than b over c. So, and since this is a uniform distribution, this just becomes b over c. So b over c times x minus p. When I maximize this, the c is constant, so it doesn't matter. And as you know, the maximizer for b times x minus p is obviously x over 2. So the maximizer had to be b over 2, and therefore c has to be 1 over 2. So the c equal to 1 over 2, which is when we have two bidders and uniform distributions, each bidder bidding half of their value is the only equilibrium in this case, right? So now let's generalize this to, okay, before that, but this doesn't, so now let's go back to this. I think I need to put this, okay. So let's just consider this example, two bidders uniform, and think about whether first price auctions or second price auctions is better for the auctioneer from an ex post perspective, ex post, right? For that, like the given values. And it's very easy to see that there are cases in which the second price auction better, and there are cases in which the first price auction is better, right? So let's consider bidder 1 has value of 0.8 and bidder 2 having a value of 0.7. That in a second price auction, the was this the computers? Okay, yeah, sorry. That will be that. So in a second price auction, they are both bidding their values, so therefore the selling price will be 0.7. Whereas in a first price auction, each of them will be bidding half of their values, which is bidding 0.4 for bidder 1 and 0.3 for bidder 2, and therefore the revenue selling price will be 0.4. So you see here the second price auction is generating a higher revenue, whereas if the values are 0.1 and 0.8 and 0.1, then in a second price auction selling price is 0.1, in a first price auction selling price is 0.4. All right. So from ex post perspective, the two auctions can generate different revenues. But let's think about expected payments, going back to this basic formula. So a bidder with value X1 in a first price auction is winning with probability X1 because he wins whenever the other bidder has value smaller than X1, and bidding X1 over 2 that we will see in the next slide, that we showed in the previous slide. Sorry, here the equilibrium bid is half of the bid, and this one becomes just X squared over 2. In a second price auction, I win when other bidder has value smaller than my value, which is X1, and I pay the expectation of my opponent, given that my opponent has value smaller than me, which is going to be uniform between 0 and X1, therefore it's going to be also X1 over 2. And you can see they both are generating the same interim expected payment, X squared divided by 2. Okay, and this is what we will generalize in a moment. Okay, and then if you want to get ex ante expected payment of a bidder, then you would need to take an expectation over this over all X, and if you want to calculate the expected revenue, then you need to multiply this by 2 because there are 2 bidders, and if you do that, you get 1 over 3, and which is like reasonable because, like as you know, you have uniform distributions over an interval. If you have 2 random variables, then the order statistics of uniform distributions are equal distance from each other, so they are going to be like 2 points here, and they all will have the same length. So this is going to be 1 over 3. This is going to be 2 over 3. So in a second price auction, remember, since everybody's doing truthful bidding, the expected selling price should be the expectation of the second highest of 2 random variables, which is going to be 1 over 3. And this is also the case for uniform, the first price auction. But let's now generalize this. So I think I have already written this here. So now let's do first the derivation of the first price auctions equilibrium strategy. So don't look there because this is actually like basically this formula is given here, and then this simple proof is confirming that this is an equilibrium in a first price auction. But now let us drive the equilibrium in a first price auction. Okay, so we have n bidders, value distributions are f, and G is defined like this. So now let's consider the maximization problem of bidder 1. So any bidder. So I'm not going to write 1 to I'm going to just write x. So if I have any bidder, okay, who has value of x and is thinking of bidding b, what will be the expected utility? U of xb is x minus b. In the case of winning, I will consume the object, and my value is x, and then I will pay b. This is the first price auction. And I'm going to write this as G of beta inverse of b. Why this is the case? Because basically I am considering a symmetric environment, and I am focusing on a symmetric and monotone equilibrium. All right. So I say that we have n bidders, and they all follow some beta, which is strictly increasing. Okay. So this can be shown, like in some papers, that this has to be the case. This is the unique equilibrium, but let's ignore that. And let's just conjecture a symmetric equilibrium that every bidder is using the same strategy beta. Okay. So these are all other bidders, right? All the rest of the n-1 bidders are bidding according to this. And I'm considering bidding some D. When do I win? I win when this is like beta inverse of B. All of the other bidders have values smaller than beta inverse of B. Is that correct? Because this is a monotone strategy and this is a symmetric strategy. Therefore, the probability that all of my opponents have values smaller than beta inverse of B is G of beta inverse of B. All right. Is this clear? All right. So now, if I try to maximize this, a necessary condition in a like a interior solution has to be that when I differentiate this with respect to B, okay, this has to be maximized when B is equal to beta of X. So what I will do is I'm going to differentiate this with respect to B and set equal to 0. Okay. And if I do not know concavity of this problem, this may not be enough, but this is basically like after solving this without using concavity, we can actually confirm that it's an equilibrium, but that's going to be the next step. So let's differentiate this with respect to B. So we have a product, right? So two functions here. So the derivative of the first part is just -1 times the second part, G of beta inverse of B, plus the first part, X minus B, times the derivative of the second part, capital G of beta inverse of B. So let's denote the G prime by small g. Then the derivative of this one is G of beta inverse of B times the derivative of inside. What is the derivative of an inverse function? It is the derivative 1 over the derivative of the original function evaluated at that point, right? So like when you have a function, right? So it's a function, the tangent is going to become like the cotangent of inverse function. So the derivative of beta inverse of B is beta prime of beta inverse of B. So this evaluated at B is equal to beta of X has to be 0. This is a necessary condition for this to be an equilibrium, right? But when I have B equal to beta of X here, then all of the beta inverse of B's become X, right? So then I can rewrite this one as minus G of X plus X minus beta of X times G of X divided by beta prime of X has to be equal to 0 for all X. So this is a differential equation, but you know, sometimes like differential equations doesn't have good solutions, but as you will see, like let's keep this and let me erase the other parts. If I multiply both sides by beta prime of X and take the negative parts to the other side, what do I get? I get, okay, let me do it slowly. So minus G of X, beta prime X, plus XGX minus G of X, I'm sorry, XGX, beta, G of X, beta of X is equal to 0 for all X. Now, if I take the negative parts onto the other side, then I get XGX is equal to GX beta prime X plus small gx beta X. But now the nice thing is that you can see that this is a derivative of the product, right? So this is d dx gx beta X, right? Because if you take the derivative of gx beta X, you get gx beta prime plus small g beta, right? Then if you integrate both parts, then you get integral from 0 to x y gy dy is equal to gx beta x plus a constant of integration, but you can see that this constant of integration is going to be 0 because a bidder with value 0 has to be bidding 0 at the equilibrium. So this constant of integration becomes 0. So therefore, you solve the equilibrium as this one. Beta of x is equal to 1 over gx, integral from 0 to x, y gy dy. And you can see that this is exactly equal to the expectation of the highest of n minus 1 variables, subject to this highest is smaller than your value. So this is our only equilibrium candidate. This is a symmetric equilibrium in a first price auction, but this is an equilibrium. This only solves for the first order condition. And since we do not know the concavity of this problem, this may be a local minimizer or a maximizer, but we wouldn't know that this is a global maximizer. So then this simple proof actually will show us that now this is an equilibrium. Any questions about this part? Maybe I went a little bit too fast here. Yeah.
So I don't know if this is a valid question. So when you derived this inequality in the middle, you point out that the right hand side is indeed the derivative of this gx times beta x. And so was there a reason that you should have expected this to be possible, or is it just somehow it works? I don't have any intuition.
Yeah, so it's like most of the time you have some, whenever you have differential equations, right? So most of the time you are not like, you don't get a closed form solution. But in this case, I think this is due to basically we already know that there will be a closed form solution because of Revin equivalence theorem. It's like we confirm that this can be done like in this first order approach way.
I see.
Because like basically like the in today's class and also next class too, we will establish a very general Revin equivalence theorem, which necessarily would mean that basically in a first price auction, your bid should be your interim expected payment in the case of winning in a second price auction. So this has to be the equilibrium.
I see.
Revin equivalence theorem, and just like follows this. Okay.
I see. Okay.
All right. So let's confirm that this is an equilibrium. In order to do that, let's consider a slightly different method. So rather than thinking about like I have a value of x and I will bid b and I will have like some conditions on b, let's think about like a revelation principle idea that let me consider a bidder whose value is x, but who is thinking of bidding as if this person's value is some other value z. Okay, so now I'm going to write this one as the utility of a bidder whose value is x, but who bids as if his value is z. So if I can show that z, this expression is maximized when z is equal to x, then that would mean that it's an equilibrium, right? Because I wouldn't be better off by doing anything else. Of course, there is this other path, like, what happens when you actually bid higher than everybody else or lower than everybody else, but you can actually also say that these are not reasonable. So like basically not mimicking any other type will be enough to show that there is no global deviation. Okay. So what is the utility of a bidder whose value is zx, but who bids as if her value is z? If I bid as if my value is z, then the probability of winning is gz, right? Because I win, I assume everybody else is behaving according to the equilibrium strategy beta, right? I'm doing a Bayesian equilibrium calculation here. The probability of winning is when everybody else has values smaller than z, and that's given by gz. And then in the case of winning, my value is x, and my bid is beta z. So this is my utility. So now let's substitute this beta of z here inside. And as you can see, beta of z will have the first term 1 over gz, and this will cancel with this one. So the first term is gz times x, and the second term is just this canceled and this part, right? So it is gzx minus 0 to z y gy dy is the expected utility of a bidder with value x and bidding as if her value is z. Now, what I can do is here I can do integration by parts. All right. So So I'm just gonna rewrite this part. Integral 0 to z y gy dy. And if I call this basically in integration parts, remember the formula is like u v is equal to integral u dv is equal to uv minus integral v du. This was like the general integration by formula, right? So if I consider my u v as g, capital G, and u as y, I can write this one as y times capital Gy minus integral from 0 to z, like without this is without indeterminate, like this is the case, right? Y gy, then capital Gy Vy, right? And when this is from 0 to z, this will be evaluated from 0 to z as well. And if y is equal to 0, this just becomes 0. So this just becomes z gz integral from 0 to z gy dy. And this is summarized here. Okay. This just like this minus becomes a plus because there is already a minus sign here. Is this clear? So this is just integration by parts. And if you, so what I want to show is that I want to show that truthful bidding, basically, right? So this is like a direct version of a first price option. Truthful bidding is better than bidding something else, right? So what do I look at? I look at the difference between the utility of truthful bidding and the difference between the utility of truthful bidding and bidding something else. And if you just calculate this, again, let's do that. Pi xx minus pi cx. All I have to do is I'm going to write this when z is equal to x, and this first part becomes 0, and the second part becomes just 0 to x gy dy, and minus that expression. And you can actually have these two parts. Okay, so let me go slowly, and this just becomes gz x minus c minus 0 to z gy dy. Okay, and then you can combine these two as this one, and these two becomes just this one. All right. So now we can finish this proof by a picture. Okay, this is a nice thing, which is basically if you look at this expression on the previous page, let me summarize it here again. Sorry. Gz z minus x minus x to z gy dy. And if you look at basically the distribution G from 0 to highest value level W, this is going to be a monotone increasing function, right? And if you consider Z to be higher than X, Z to be higher than X, then you can see that this expression is going to be this rectangle, whereas this expression is going to be the area underneath G between X and Z prime. And therefore, since this rectangle has a high, by definition, a higher area than the area underneath G over this interval, this is going to be the result, and this is going to be always positive. Whereas if you consider the case in which Z is smaller than X, denoted by Z double prime, then you can see that the reverse of this, negative of this expression, is the difference between the area underneath G between Z double prime and X and this rectangle, and therefore it's also positive. All right. So this shows that basically both for mimicking an under type or an over type is worse, and therefore in the previous slide, this is an equilibrium of the first price option. All right. Any questions? I have my notes here. I want to make sure that.
Can you just show the same thing that becomes open in your option?
OP auction, we will talk about OP auction. You ask about OP?
Yeah.
Okay. Yeah. So we will talk about OP auction as the first application of revenue equivalence theorem. Okay. So what else?
So what was the restriction on the F action to?
Nothing right now. No restriction. It's like a atomic continuous differentiable. That's it. But we do not need like a regulator or anything else.
I assuming strictly positive testing.
Mm-hmm.
And so for that picture,
Yeah.
it seems that even if G is a constant function, the D works. But
The G cannot be a constant function, right?
no. I mean the part even if part of the G function is constant, this particular step of the proof seems to work.
Oh, okay.
But is there any other place where you use the strict positivity?
Yeah, I'm pretty sure. Like there are of course like existence results and some other papers about like the first price auction equilibrium with assumptions other than the standard like smooth increasing distribution functions. I'm pretty sure these similar result hold for more general settings, but I cannot really tell you right now like what exactly is needed. But that's a good observation. So like if this is not a strictly increasing function, but it is like a weakly increasing function with some pools and stuff, the same argument will work here. Yes, I agree. That may indicate that actually this may be for these cases too, but I cannot really tell you that this paper is established that. Okay, so there are maybe let's do a little bit some play with this formula to get some things. Remember, this was the first price auction equilibrium strategy, and we can rewrite this one as so. If I take capital G inside and do basically again the same integration by parts that I had done previously. Then you can write this whole thing as this one. So remember, like in the previous, like the thing that I raised, I used some integration by parts. If you do the same integration by parts, you can rewrite this one as this one. And you can, so capital G is f to the power n minus 1. So this just becomes x minus fy divided by fx to the power n minus 1. And this is like another way of seeing something about like bit shading, how much I should shade my bit, right? So in a second price auction, truthful bidding is a dominant strategy. In a first price auction, truthful bidding is a terrible idea, right? You will get zero payoff. So you need to bid lower than your value, but how much lower will depend on the competition. And this just becomes basically a very good way of seeing that as the competition gets higher, you will shade your bid less and less. Because fy divided by fx, remember x is constant here, and fy is increasing till fx. If you take the to the power n minus 1 of this, it's going to get smaller and smaller, and therefore you will bid, your bit shade will be smaller and smaller as n gets larger. It will never get to 0, but it will be you will bid more and more as n gets larger, which is like easy to see from here. Okay. And okay, so expected payments. So I erased the interim expected payment expression for a second price auction, right? But as you can see, interim expected payment in a first price auction will be also the same. Okay, so what is my probability of winning? It is capital G of x times, in the case of winning, I will pay my own bid, which is given by this. So capital Gx and 1 over Gx cancel out, and this just becomes interim expected payment. And therefore, basically, these two options result in the same expected revenue. Okay. But this expected revenue is also indicated earlier by this example that I gave you. Remember, like the ex post payments can be different. The price distribution in a first price auction and a second price auction is different. All right. So what I will do right now is I'm going to write down, okay, the expected revenue in a first price and second price auction. Okay, and then talk about the price distribution and show that they are different. And therefore, like this is not in the slides, so you just need to follow me here. Therefore, for instance, you will have the extra result that if the bidders are risk neutral, but the auctioneer is risk averse, then the auctioneer actually would strictly prefer a first price auction to a second price auction.
Or maybe this is going to be a very ill-formed question, but so when I see this proof, so use integration by parts and which I usually have very little intuition about, honestly. So basically, this is a sort of special case, so to speak, of the revenue equivalence, like you mentioned. Are they kind of showing in the sort of parallel manner here, or are they following a different?
So I know that I'm kind of like going slow, but I think it's important to get to these steps. Basically, like in the second half, we are going to establish a more general revenue equivalence theorem. So this is just a revenue equivalence between first price and second price auction. Next step will be to show that for all standard auctions, not just first price and second price, but all standard auctions, which means all auctions in which the highest bidder wins, and everybody is using the same symmetric monotone strategy, which means that the outcome of these auctions, it could be all pay, it could be the third price, it could be hybrid, it could be war of attrition, many others. Assuming that these assumptions hold, they will all generate the same expected revenue, ex-ante expected revenue. And the next step will be to show that basically, due to revelation principle and incentive compatibility, the interim expected payments basically are perfectly determined by the allocation rule. Therefore, like the next result will tell you that if the allocation rule is efficient, up to this constant of integration, which is determined by the expected utility of the lowest value type, up to that constant, they all will have the same expected revenue. And a generalization of this will tell you that basically you don't have to assume that the allocation is efficient. Maybe you have two auctions, their allocations are not efficient, but their allocations at equilibrium are the same. The payments have to be the same because the shape of the Q function, the allocation function, perfectly determines the shape of the T function, the transfer function, up to the constant.
Right.
Okay.
I see.
So we will do this in steps. We are taking like baby steps.
Sure. So I guess my question is actually, so I also remember that vaguely, unfortunately, the general revenue equivalence theorem is also using something like maybe integration part or something, envelope theorem, I see. Envelope theorem. So when I see this version of the revenue equivalence that we just saw, are they roughly following the same logic here as the general one, or it's totally different actually? Because
once you know the general results,
then we know the shape.
These are not necessary, but I like them because, like for instance, whenever you are working on different auction problems, right? It doesn't have to be first price or second price. You almost always will have some differential equation that using some changing order of integration or other methods, right? So the integration by parts is helpful and will give you the result. So like, doing applications of integration by parts and changing order of integration and other tricks is good to know. So that's why I see it as like a good applications of this. But also, like I admit that this is like a special instances of that some result that will come later and which will actually have an easier proof.
I see. Okay, that's helpful because usually I know.
That's actually like something like this can be seen as like a sanity check. So what I'm going, we already established revenue equivalence theorem, right? So for between first price and second price only right now. But what I want to do is I'm going to do some mathematical, plays in which I will also now use like some other techniques to establish that basically the selling prices of the first price auction and second price auction are the same. We'll have the same expected result, which is like obvious, but they will have a different shape. Okay, so, all right. So, in a first price auction, MIX, and also in a second price auction, we establish that interim expected payment is G of X times beta I of X, which is equal to integral 0 to X, Y, G, Y, dy. Okay. So this is the interim expected payment. Now, let's look at, for both of these cases, the ex-ante expected payment. So not N of X, but just M, which is ex-ante expected payment of one bidder. Okay. So what do I need to do? Basically, I need to take the expectation of this for all X. Okay. So let's say that the values are between 0 and 1 or 0 and W, doesn't really matter. So let's say 0 and W because BJ uses 0 and W in the 0 to W. M of X, let me ignore this. Like this, let me call this MX. Okay. MX dfx or small fx dx. Sorry. Which is equal to 0 to X, 0 to W, I'm sorry. Integral 0 to X, Y, G, Y, dy. Then fx dx. Okay. So now what I'm going to do is I'm going to use another trick, which is changing the order of integration. Okay, so like the previous one was important. This also is helpful in many auction applications. So whenever you do this, it's always good to kind of like have a small picture in mind in order to make sure that you are doing this correctly. So here X varies from 0 to W, right? So this is, let's say that this is the X-axis, and this is the Y-axis. Y varies from like 0 to X, but since the highest value of X is W, Y also varies from 0 to W. All right. So basically, what you are doing is in this integral, you are covering this part. Okay, you are covering this part. So let's now do the same double integral, not X in the outside and Y in the inside, but Y in the outside and X in the inside. So if you do that, Y also varies from 0 to W. So this is like changing order of integration. This is also a very commonly used trick to get something nicer. This also you will see like for the optimal auctions, when you are doing Meyerson's optimal auction in the next class we are going to do, we will do the same here. So Y will vary from 0 to W, but now I will take the X part inside. So I'm going to have now when I want to also cover the same area, not this way, but this way. Now Y will vary from X to W because Y should be smaller than. I'm sorry. This is going to be Y. X should be higher than Y, right? So X. Lowest value of X has to be Y, and then it can go all the way up to W. Then fx dx y gy dy. Is this clear? Right. So this was the important part. For me to cover the same area, since Y is smaller than X here, now X has to be greater than Y here. And now I can write this one as 1 minus f of y, right? Because like integral from Y to W is the probability that Y, the X is greater than Y. So this just becomes 1 minus f. So therefore, this whole thing is now this double integral became a single integral. Integral from 0 to W, 1 minus f of y, y small gy dy. So this is the ex-ante expected payment of one bidder. And what is expected revenue? Expected revenue is just n times this simply, because we have n of the bidders and we just simply add them up. So expected revenue then is n times integral 0 to w y 1 minus f of y gy dy. Okay. Now I'm going to erase the rest, and I'm going to do also the following. This is also a sanity check. Okay. Like this was done basically by like an ex-ante expected payments, and then therefore reaching to the expected revenue from the equilibrium deviations, derivations of first price auction. But we can get to the same, we should be able to get to the same result as a sanity check with this following idea. So remember, in a second price auction, dominant strategy is everybody is bidding their values, right? And then the winner is going to pay the second highest bid. Therefore, the expected revenue in a first price or a second price auction should be the expected second highest of n independently random variables. So I'm going to show basically that ER is also equal to expectation of the second highest of n random variables. Okay. Okay, so this is also a nice math exercise because this involves knowing something about conditional probabilities, conditional expectancies, and order statistics and so on. All right. So if you don't mind, let's do that too because I like it. Okay. So I want to basically take the expectation of the second highest of n independently generated random variables. Okay. So how do I do that? I need to first calculate what is the probability that the second highest of n, I'm sorry, n here, I always confuse n here, second highest of n is smaller than some value y. Okay. So I can have this in two ways, two distinct ways. One of them is if the highest is smaller than y, then I'm done, right? So the second highest is obviously smaller than y. So it is f of y to the power n. But I can also have one of them has actually higher than y, is higher than y, and the rest of them are smaller than y. So the one of them being higher than y is 1 minus f of y, and the rest of them smaller than y is f of y to the power n minus 1. Am I done? Is this the correct expression? So I'm trying to make it more interactive. No, because I can do this in n ways, right? I can choose the bidder who can be chosen as the highest in n different ways. So I need to multiply this by n. Now I'm done. Now this is the probability that the second highest of n random variables is smaller than some value y. So if you do this, so this one becomes like, this is like f of y here and f of y to the power n minus 1 here. So these together will make you f of y to the power n. I have f of y to the power 1 here. So you can combine this one as n times f of y to the power n minus 1 minus n minus 1 times f of y to the power n. Okay. Sorry. Let me continue. So now this is the distribution function. Now let's us calculate the density of this. So I'm going to just take the derivative of this, which is equal to y. So what is the density? Because basically, in order to calculate this expectation, I need to have an integral of y times the density, right? That's how. What will give me the expectation? So the density is the derivative of this, which is n times n minus 1 times f of y to the power n minus 2 times small f of y, that's the derivative of the first part, right? Minus n minus 1 times n times f of y to the power n minus 1 times the small f of y. Okay, now I have many things in common, n minus 1 here, n minus 1 here, fy here, and then like I have this also f of y to the power n minus 2 in common as well. So this one is n times n minus 1 times f of y to the power n minus 2 times 1 minus fy, because this has an extra fy in it, right? So 1 minus fy times small fy. Okay, so this is density. And then this one is nothing but this times y dy. Okay. Now let us confirm that this is equal to this. And you can confirm it because you can write this one as, remember, small g is the derivative of the big G. And therefore, this is equal to the dy f of y to the power n minus 1, remember? So therefore, this is n minus 1 times f of y to the power n minus 2 times small fy. Now let us match all of them together. So there is an n here, n here, n minus 1 here, n minus 1 here, f of y to the power n minus 2 here, f of y to the power n minus 2 here, small fy here, small fy here, y here, y here, 1 minus fy here, 1 minus fy here. So they are equal. So let's so this is a nice exercise. I like it. But keep in mind that let's go back to, like, for instance, two-bidder uniform distribution case. If you think about expected price distribution, this expected selling price in a first price auction and a second price auction, although like interim expected payments are the same, if you think about ex post selling prices distribution, they are obviously not identical, right? Because think about in a first price auction, selling prices can vary between 0 and 1, right? I'm sorry, in a second price auction, the selling prices can differ between 0 and 1. Because like if my value is 0.99 and your value is 0.98, then I will pay 98, right? Whereas in a first price auction, the highest price will be at most 0.5 because everybody is bidding the half of their values, right? So if you look at like the expected selling price distribution, the distribution for the selling prices, which is actually what we calculated earlier for the second price auction, it is like something like this for a first price auction, second price auction, 0 to 1, whereas it is something like this for a first price auction. So it's 0.5. This is like SPA selling price distribution. This is FPA selling price distribution. Although they have different shapes, the expectations of this is the same. Therefore, actually, like expectation by, again, if you do integration by parts, you actually can write the expectation in a different way, and this would necessarily mean that the area of here and the area of here has to be the same. Okay. So one last thing, which is, I think, like nice thing that before we move on to reserve prices and almost end the class, which is that I want to say that the selling prices in a second price auction is going to be a mean preserving spread of the selling prices in a first price auction. What does a mean preserving spread mean? It means like actually a different version of a second order stochastic dominance, right? So this means that they have the same expectation, but the second one has a higher variance. And therefore, we know from the classical resulting, the decision theory or game theory is that any risk averse, person would prefer the less random distribution. Therefore, a risk averse seller would actually strictly prefer a first price auction than a second price auction. So this is the next result. It is not in the slides, but I want to tell you.
Actually, just to make sure to the bidders are still risk neutral. So we are talking about risk actually on that.
I'm just telling you something about the fact that second price auction price distribution, price means like selling price distribution, is a mean preserving spread of the first price auction. So what does it mean? It means that conditional on the fact that the event that the first price auction price was some particular value P, what is the expected selling price in a second price auction? And it will turn out to be also equal to P. And the second price auction will have a more variance. And therefore, it's going to be like second order stochastic dominated by first price auction prices. Okay, so the proposition is distribution of equilibrium prices in a second price auction is a mean preserving spread of one APA, and therefore a risk averse seller prefers APA over SPA. So proof. This is also like a nice and like a short proof. Okay? I like. So let's say that let's remind ourselves that the selling price in a second price auction is nothing other than YN2, which is the actually calculated density for it in the previous exercise, right? Whereas the selling price in a first price auction is beta of YN1. So the selling price in a first price auction is the beta applied to the highest value, whereas in a second price auction, it is the second highest value. All right. So what is the expected R2, our second price, given that R1 is equal to some P, some price? It is expected value of YN2, given that Y1N is equal to beta minus P, right? Because like for the highest, for the price in a first price auction to be P, the highest value in this environment has to be beta inverse of P. Is that correct? But now I have this following trick, which I also like. I can argue that this is equal to expected value of Y n minus 1, given that Y1 n minus 1 is smaller than beta inverse of P. Why? Because like if I know that the highest is exactly equal to beta inverse of P, okay, out of n, I know that the highest out of n is exactly equal to beta inverse of P. That immediately tells me that the second highest of, like basically all the others are smaller than this. So among the remaining ones, the highest is strictly smaller than this. Or weakly, doesn't matter. Okay? So, and then basically, like once you basically, this is now a known. So Y1N equal to beta inverse of P is a known. Now take this out from the equation and think about the rest of them. For the rest of them, you now know that they all are smaller than beta inverse of P. It doesn't matter if it's like weak or strict. And then the second highest of n becomes the highest of n. But now this is just nothing but like, this is like, remember the beta of x, beta in the first price auction of x was expectation of highest of n minus 1, given that this one is smaller than x. Now let's substitute this here. This is beta of beta inverse of P, which is nothing but by P. So this shows that like the second price auction equilibrium prices is a mean preserving spread over the first price auction equilibrium prices.
Sorry.
Yeah.
What is the definition of mean preserving variance?
Yeah.
I think we also need to show that variance.
Yeah.
So how?
No, this is incomplete. This is yeah. This is just that part, and then the second part is basically you say that like the previous picture indicates that. I'm not giving you the complete picture, but right now in the previous picture I was telling you that the values are between 0 and 0.5 in the first price auction and 0 and 1 in the second price auction. So it obviously has a yeah.
Oh, sorry, maybe I'm
Yeah.
You know,
So this
so that the
condition-
variance is weekly larger, is it
Sorry?
obvious because the variance of the second price,
No,
payment
it
is,
is not weekly. It is, I think, okay, let me finish the question. So
I
I
actually
think,
saw
you
that.
know, I think under this, under like continuity, the assumptions that we have made so far, the variance in a second price auction is strictly.
Yeah, oh, but the fact that it's weekly larger,
Mhm.
is it obvious by this argument? Because you fix the.
Yes, yes, it is
yeah.
weekly larger is obvious by this.
Obviously, because
You could also
just a
potentially
constant.
for instance, if the reverse also holds, which doesn't, of course it doesn't, like this would mean that they are equal.
Right,
But
right.
there is no possibility that they
I
are
just
equal.
wanted to make sure.
Yeah.
So here the argument is that the first price, the actual payment is fixed at some
Yeah.
value P, and then you still have
Yeah.
some variance.
Yeah.
So I mean,
Yeah.
that's a small variance.
Yeah,
that you can
and
get.
expectation is the same. So like they are mean preserving, and it has to be because of revenue equivalence theorem or the
So do we know which auction format minimizes the variance among the ones that are equivalent to revenue equivalent to these options?
Like for instance, all the option will obviously have a smaller variance, right? Because it will actually be like the highest value will be smaller. Yeah, because like I believe so. So that's a good question. That's I never saw any paper that asked this question. So maybe it's a simple exercise that one can show. Maybe it has been studied in the literature. Yeah. Good
I
question.
see. Actually, I have the same question. So I was actually wondering. So I am trying to understand this proof. So you are saying, so it looks like a first price has a very good property that you kind of know how much you pay.
Yes.
Conditional winning. So that
Yeah.
kind of like makes the sort of variance more. I
Yeah.
thought, but then this does not tell you that it's the other format like pay auction is a mean preserving spread, because actually this equality doesn't hold for the
All the option I can
for
check.
the
But I think the simple answer is I do not know the answer.
I see.
Like really, this the like this
Oh,
is
but when-
standard. Like in thinking of like since first price auctions and second price auctions are very well studied, the question of risk averse seller, which one is better, is a very reasonable question, and it can be answered in a very simple way. So this has been known. It is in VJ's book, but I didn't see like any papers that ask this question of what is the actually there are papers that at least give some partial answers to optimal options with risk averse sellers, right? There are, I think, papers by Maskin, but they could be working on like more general mechanisms, not just options, but like arbitrary mechanisms. And I need to check that. And if the answer there is I can auction, then that's an answer to your question too.
I see.
Like, yeah. I think like the optimal mechanisms for risk averse sellers has been studied by I don't remember, like Riley and Samuelson or some papers I need to check. Yeah. Anyway, but I have 10 minutes. I'm a little bit behind, but I don't need to like rush and finish everything. So it's better if you go slow.
Yeah.
Sure.
Could you remind me of the definition of efficiency?
Oh yeah. I forgot to tell you like what is here. So this is like expected revenues is the same. We mentioned this so many times. Selling prices are not the same. We just established it here. And efficiency here means like could be two things. One of them is like the social welfare, including the auctioneer. So think about that I sum up all the utilities of all the players. And if I also consider the auctioneer, then the transfers will wash out, right? So if I give any money to the auctioneer, then that's going to be received by the auctioneer. So it will be like washed out. It will be, canceled. So, and in this context, it would mean the winner is the highest valued bidder. Okay, so therefore, like both of these equilibria are monotone and symmetric, right? So like we have symmetric bidders and we have symmetric monotone strategies, and therefore the winner for both first price auction and a second price auction is the highest valued bidder. So they are both efficient. The allocations are the same. We will talk about asymmetries. That also like is going to be an important part of like the Friday's first class asymmetric auctions. And we will also consider resale there, and we will have some interesting results about the efficiency there. Okay. So let's talk about one more thing, which is like so far we consider the auctioneer to be quite, other than choosing the auction mechanism, quite inactive. But in practice, it's actually, they can also use one more thing called reserve prices. So what does the reserve price mean? Reserve price means that the auctioneer is using some auction format, but saying that I'm not going to sell, I'm going to keep the item if the selling price is smaller than some value. So I'm not going to sell less than $1,000 for this painting or something. And this is using practice. So it is important to understand the implications of the reserve prices on auctions. So the reserve price is going to be denoted by R. And so let's start with a second price auction. So in a second price auction, by the way, I think when I first mentioned the dominant strategy equilibrium of a second price auction being truthful bidding, which is bidding your value, this is a dominant strategy under more relaxed assumptions. So far our assumptions that we had private values, we have symmetric setup, and so on, right? But this argument about dominant strategies, that actually they did not require symmetry, it did not require risk neutrality, it did not require private values, right? So similarly, even with reserve prices, if you think about the equilibrium strategy in a second price auction, even with reserve prices, you would always want to bid your value. Okay, therefore the equilibrium is easier to think, and the expected payment changes though, with the reserve price. So now let's consider a bidder with value X, and there is a reserve price of R. Then we have two instances. This, and let's say that X is greater than R, because when X is smaller than R, then X will bid smaller than R and will never win the item, and right, so the payment will be zero. We only care about the bidders whose values are greater than R. And if my value is greater than R, then in terms of my payment, there will be two contingencies. One contingency is that if the rest of all of the other bidders have values less than R, then I will not pay the second highest bid, but I will pay the reserve price, because that's the definition of the reserve price. So the auctioneer is never letting the object go for a price less than R. So he will charge me R if the second highest value is smaller than R. So with probability GR, then I will pay R. And for the rest of them, if at least one bidder among my opponents have values greater than R, then this value will have a density of small gy, and I'm going to integrate this over R to X, because if the highest value among my opponents is greater than my value, then I will not win anyway. Okay. So now what I do is, in order to calculate ex ante expected payment of a bidder, then I need to take the integral of this from R to 1, right? Because if this is smaller than X is smaller than R, then payment is 0 anyway. So from R to 1, all I do is here substitute what is written in the previous page, small fx dx. And then you can see that this term doesn't have any x in it, so I can take this out. Okay. And integral of R to 1 small fx dx is just 1 minus fr. So the first term just becomes this. And the second term is here, R to 1, x to R, y, gy, dy, fx dx. And then again, the changing the order of integration trick that we had done in the earlier, if you do the same here carefully, okay, then you can make this double integral. And this is an exercise if you would like to practice changing order of integration. You can write this one as this one. Okay? So this is a double integral. By changing order of integration, this becomes this one. And therefore, n times this is going to be the expected revenue. And the main result is going to be that a small reserve price is always better for the auctioneer. Okay, so this is called the exclusion principle. So what I do is basically what I need to I will basically have two things. One of them is try to argue that when the auctioneer has some value. So far we kind of assume that this value is 0, but for this discussion, in order to make it a little bit simplistic, like the next slide will also allow for the auctioneer having some value, non-zero value. The argument will be that a binding reserve price, choosing a reserve price higher than your value, will be beneficial for the revenue. And the second one is going to be under like the monotonicity assumption for the virtual values. We are going to establish that there is a optimal reserve price that can be chosen. Okay, so and then that will be like in the second class. We will have a little bit more discussion on the optimal mechanisms. So let's finish this, and we have only 4 minutes left. So this is basically a copy from the previous slide. Okay, and now I'm going to take the derivative of this expression with respect to R. Okay, if I take the derivative of this expression with respect to R, you see that okay, so if I had more time, I would have done it like this more explicitly, but so whenever you are taking a derivative of an integral, right, you will consider 3 parts. Whether the upper part is like changing with the variable that you are taking derivative for, which is it doesn't, right? So I'm taking derivative with respect to R, so this will be 0. And for this one, I'm going to have a negative part, and then I will put y is equal to R inside and take it outside as a negative part. What was the rule? What was Lipschitz rule? What was the rule of this changing, taking derivative of an integral? I forgot the name. Leibniz rule. You use Leibniz rule, but actually this happens very often whenever you do any auction calculation. What happens is that one of the things will cancel out a big chunk of what is on the left-hand side. Okay, so like you would have seen it if I had it here. But basically, this may potentially be a long expression, but since the derivative of this, which is like negative part, when I put this R1 minus R, GR here, it actually cancels some part of it. It just becomes this. Okay, trust me, you can confirm this yourself. And then once you have this, like the lambda is equal to 1 divided by 1 minus F, which is called the hazard rate, right? So once you define a hazard rate here, you can write this one as in the second line. And then this expression, like basically for an optimal interior solution, this has to have a 0 derivative, right? When you calculate, when you set this equal to 0, G of R is never 0, so it cannot be. 1 minus F of R is never 0, so this cannot be. So this has to be 0 for an optimizer, for an optimal reserve price. And then you can write this one as this one. And as you will see, we will actually see this again in the second class this afternoon. This is like the Meyerson's virtual value. And so this means that the optimal reserve price is the price that sets the virtual value equal to 0. And very interestingly, this is independent of the number of bidders. If you have 2 bidders or 1 million bidders, the reserve price, optimal reserve price, doesn't change with the number of bidders. Okay. And
so how did you know that G of R can't be 0?
Because G of R has, when G of R is equal to 0, R has to be 0.
I thought we wanted to show that R is not equal to 0.
Oh, yeah. So good, good question. Actually, yeah, good question. So this is G of R has to be. I don't know. Okay, so good question. So this is why, like, if you read the BJ's book, actually it starts with the value to the auctioneer is not 0, but it is some value. I don't remember, like what. Let me see. X0. He calls it X0. And when X0 is strictly greater than 0, that never is a problem. But when X0 is 0, actually the picture is something like this. So actually it starts from 0. So it's like the derivative at 0 is equal to 0, but it is immediately strictly increasing after that. So we cannot pull out. I think it's in the picture or no? I think there is a book in the picture, but unfortunately. So it is something like this. So if you depict the, like for instance, 2 bidders uniform distribution or n bidders uniform distribution, the reserve price is like the expected revenue as a function of reserve price is, so it goes like this. All right. So actually there is a local, like a extreme point here, but this extreme point is not a maximizer. So what I'm doing here is not complete. I agree. G of R, like I cannot rule that out.
So when you see this differential equation,
Yeah.
so can we immediately see that when R is slightly bigger than 0,
Yeah.
then R or G of R is
Yes.
positive,
Yes.
and then this 1 minus whatever is actually
It's also
very small, very close to 1, right?
Yes,
because
very close to
it
1.
has a one,
Yes,
R.
yes. So this basically means that, like, although the derivative here is 0, this
Right.
function is actually increasing.
I see.
Okay. So like this is called the exclusion principle. The exclusion principle means that it is always better to exclude some bidders, meaning that not like basically, that they put a binding reserve price, and this will increase the revenue, and at the same time this will decrease the efficiency, right? Because sometimes you actually, although there are bidders whose values are greater than your value, you are still keeping the object. So this will not give you full efficiency. All right. So there is, okay, let's continue in this. I was slower than I hoped, but I think we will still cover a lot in this second part. Thank you. Do you have any other questions?
So what about this argument? Are the bidders are symmetric, right?
Yeah, they are symmetric, but we are going to go through asymmetries in this next class.
Okay, so when you talk about the optimal reserve price with but not the optimal mechanism.
No. So
Okay.
optimal reserve prices for the symmetric case is like the one that will be like setting the virtual value equal to 0. That's gonna be the result. But as we will see, I'm pretty sure we will have time to do that. That for in general, for like if you try to solve an optimal mechanism question for the non-symmetric cases, that the main result is gonna be that you will have different virtual values for each of these bidders, and we will need to allocate the item to the bidder with the highest virtual value, given that this highest virtual value is non-negative, right? So this is gonna be like an extension of this one.
My question
So this is gonna be personalized, basically.
Wait. My question is in between. So the distribution is asymmetry.
Yeah.
But one has to use the same reserve price to everyone.
Oh, okay. I see.
If anything more, or will you talk about that case?
So like the asymmetric value distributions, especially when you like, we will also talk about this on Friday too, because like we have this paper about asymmetric first price options, especially. It's quite complicated. So there aren't too many theoretical works. Like you will see, like even today in the afternoon, that unfortunately there is no closed form solution to the pair of linear differential equations. So maybe there are some papers who had worked on like there is a requirement to use the same reserve price even when the bidders are asymmetric. Like at least in the first price auction setup, this is very difficult to deal with. But for the optimal auction setup, maybe some papers have done it. I need to check. All right. Okay. So
Good. I think we should feed Isa. So let's stop the morning lecture for now. Okay. So thank you very much.